So we're going to continue our work here on factoring the difference of squares and some of the other cases that you might see and recognizing when you have the difference of squares. So we're going to factor the following expressions. The first one is x squared y squared minus 1. Okay, so first of all, it's recognizing x squared y squared as a perfect square, right? So if you have xy, the quantity xy, quantity squared, that's the same thing as x squared y squared, okay? And then also recognizing that 1 just by itself is also a perfect square. 1 squared is 1, right? Square root of 1 is 1. So we can factor this as the difference of squares. Xy plus 1 times xy minus 1. Of course, if we check this going the other way, xy plus 1 times xy minus 1. Xy times xy is x squared y squared. Xy times negative 1 is minus xy. In the inner term, 1 times xy is xy. And 1 times negative 1 is minus 1. Okay, so we see how that works. X squared y squared minus 1, exactly what we started with. That middle term cancels out. Okay, so this next one, 9y squared minus 64z squared. I notice that 9 and 64 are both perfect squares, as is y squared and z squared, right? So you can think about that as being 3y quantity squared, right? Minus 8z quantity squared. Right, okay, so then when we factor this, we're going to have 3y plus 8z times 3y minus 8z. Yep, fully factored. And folks, checking these, is it really necessary every time? No, I like to do it here in the video just to show that it all works, and I catch my mistakes if I make any. So 3y plus 8z times 3y minus 8z, and it gives us all that good foiling practice. 3y times 3y is 9y squared. In the outer term, 3y times negative 8z is minus 24yz, right? And in the inner, 8z times 3y is plus 24yz. And the last, 8z times negative 8z is minus 64z squared, right? Okay, and so again, the middle term, negative 24yz plus 24yz goes away, right? So we're just left with 9y squared minus 64z squared. Nice. Okay, now, this next one doesn't look like the difference of squares at all to me right now, but let's look at it. So it's 2x to the 7th y cubed minus 200x to the 5th y to the 5th. Okay, so I notice right off the bat, with all that going on, I'm asking myself, is there a GCF or greatest common factor that we can factor out of that before we even think about whether this might be the difference of squares? So I'm looking at 2 and 200, and I said, well, I can pull a 2 out, right? So we'll do that. And what else can we pull from the 2? Both of them have x's, right? And how many x's can I pull out? I can pull out 5 of them. X to the 5th, yes? And then look at the y's. I've got y cubed and y to the 5th, so I can pull out a y cubed. Okay, so if I pull 2x to the 5th y cubed out of 2x to the 7th y cubed, I'm going to have x squared left, right? So think about that. If I multiply x to the 5th times x squared, I get x to the 7th, right? And that would give me the original term, 2x to the 7th y cubed. Okay. All right. Now the second term, if I factor a 2 out of 200, I'm going to be left with 100, right? So I'm factoring all of x to the 5th out. And then I have y to the 5th, but I only want to take 3 out, so I'm going to have 2 that remain, right? Y cubed times y squared is y to the 5th. Okay, so when I factor that GCF out, I'm going to have 2x to the fifth y cubed times the quantity x squared minus 100y squared. Okay, x squared minus 100y squared is the difference of squares, right? Because 10 squared is 100. So leave that GCF alone, 2x to the fifth y cubed. And now we're going to factor that difference of squares into the product of two binomials. Okay, so you want to think about that as x squared minus the quantity 10y squared. Yeah, so you're going to have x plus 10y times the quantity x minus 10y. And that's fully factored. There's nothing more we can do to it. So let's check it. We'll go back the other direction and see if we get the original statement that we started with. So 2x to the fifth y cubed times the quantity x plus 10y times x minus 10y. I'll take it down here since we're running out of room. 10x to the fifth y cubed. We're leaving that first GCF alone. We're going to do the FOILing first. X times x is x squared. X times negative 10y is minus 10xy. 10y times x is plus 10xy. And 10y times negative 10y is minus 100y squared. Okay, so again, that middle term goes away. 10x to the fifth y cubed times x squared minus 100 y squared. And you notice already you can see it, right? The work that we did to pull out the GCF, we're just seeing this in reverse, right? So I'm going to distribute the GCF back through. What are we going to have? X to the fifth times x squared is x to the seventh, y cubed, right? And then for the second term, when we distribute the GCF through there, 2 times 100 minus 200, x to the fifth, y cubed times y squared is y to the fifth. Is that what we started with? Yes, it is. Very good. Now, one other type that you may see that I want to talk about, because we've been talking about variables that are literally just squared, but you can have higher powers that are also perfect squares. So for example, r to the fourth minus p to the 12th. So if we just look at the exponents alone, 4 is a perfect square and 12 is not a perfect square, but really any exponent that is even has a factor of 2 in it, right? Which means that you can write it as a perfect square. I'll show you what I mean. So with r to the fourth, that's the same thing as r squared squared, right? Power to a power you multiply. And with p to the 12th, we can write that as p to the sixth quantity squared, right? Again, power to a power you multiply. 6 times 2 is 12. So we really do have the difference of squares here, okay? So thinking about that, we would have r squared plus p to the sixth times r squared minus p to the sixth. Okay. Now, the question I would ask here is, are we done? Could we factor this even further? So this is another thing that you need to look for. Sometimes when you factor using difference of squares, look at the remaining factors. You have another binomial there that's a difference. I have r squared minus p to the sixth. Both of those exponents are even, right? This one right here I could write as r squared minus p cubed squared, right? So once again, we can use the difference of squares. Now r squared plus p to the sixth. Remember, we cannot factor the sum of squares, only the difference of squares. So it's only that second binomial that we can get anything more out of. So we're going to have r plus p cubed times r minus p cubed. And that is fully factored, right? No more difference of squares to be found in that statement. Okay, so I'm going to check this. Now, I'm writing this out again. Quantity r squared plus p to the 6 times the quantity r plus p cubed times the quantity r minus p cubed. So I've written this out again. R squared plus p to the 6 times r plus p cubed times r minus p cubed. Okay. You can FOIL this in any manner that you want. You could FOIL the first two and then the last two. I'm tempted to do it in the order in which we put it together, or rather pulled it apart. I'm going to leave the first quantity of r squared plus p to the x by itself, and I'm going to FOIL the last two binomials here. So r times r is r squared. R times negative p cubed is minus r p cubed. P cubed times r is plus r p cubed. And p cubed times negative p cubed is minus p to the 6th. Okay, so we have r squared plus p to the 6th times r squared minus p to the 6th, right? Our middle term goes away. So now we're going to FOIL that last piece. R squared times r squared is r to the 4th. R squared minus p to the 6th is negative r squared p to the 6th. P to the 6th times r squared is plus r squared p to the 6th. And p to the 6th times negative p to the 6th is minus p to the 12th, right? And of course those middle terms go away with the r squared p to the 6th, and we're just left with r to the 4th minus p to the 12th. All right, so this was a really valuable example, I think, because not only because you were dealing with exponents that were higher than 2, but also when we actually used the difference of squares to factor it, we came up with another binomial that was also the difference of squares. So always look for that. So when we say to factor something, factor it completely, right? Expand it as much as you can.